So, and also, I recall that last time our goal was to define solution of the Young-Baxter equation. And to do this, we have introduced the notion of an R matrix for our algebra. Maybe so. Maybe we say that quasi-triangular of algebra of algebra A, so with invertible antipode, which is endowed with an R matrix. Maybe I recall from last time. So what is an R matrix? This is an element R belonging to A tensor A. Such that, so R delta is delta of R. Delta, this is a coproduct of A. And you have identity of R is R13, R23, identity R13, R12, and epsilon tensor identity of R is identity epsilon of R. So we have seen this last time. Maybe I recall the graphical calculus. So what means this equation in graphical terms? So the first one is if I multiply R with delta, like this, it is, first I use the opposite of delta and multiply by this R. Now, if I have this R and then the coproduct is, so R 13, R 13, 23, then this axiom is R. So R13. And finally, the last axiom is this is the unit, and this is R. Okay. So we have seen this last time, and maybe I recall from last time that then R is invertible in the algebra A tensor A with inverse computed as follows. It is computed by S tensor identity of R, identity tensor S inverse of R. Okay. Now, if we have, as I said last time, for M, N, if you consider A modules, or maybe before this, I use some notation. If M is an A module, left, I will work with left A module. This is a map from A tensor M to M. We denote it. It's denoted like this. A tensor M to. And the axiom of a module says that. So if you take two elements of A, then you first multiply the action of a product is twice the action. So A, B, M is A, B, M. And 1M is M means. So A, M, M is like this. A, M. And the unit acts on M as the identity. I just rewrite the axiom in graphical terms. Okay. Now, we defined last time for left A modules M and N. We define C M N as follows. M, N, N, M. So this is from M tensor N to N tensor N. So for the last time, I will explain the last time, I recall for last time what it means. So if R, you can write it as like this. As a finite sum like this. And M in M, N in N. Then C M N of M tensor N. If I plug elements so AI acts on little m, BI on little n, then I flip. So it is a sum from I, so BI n, also AI n. Okay. And last time I gave a property. So I will rewrite it. So we have the following property. So first, CMN is an A linear isomorphism with inverse C M n inverse is computed like this. So you go to n tensor m and you put R inverse. I recall that R is invertible like this. Go to n tensor m. And second, maybe I will say this property, CMN is natural in M and N. So what does it mean? For any A linear homomorphisms, so morphisms. So I will denote them by F from M to M prime, G from N to N prime. So we have that. What can I do? C M prime N prime of F tensor G is G tensor F CMN. First, write this property. Okay. So let us quickly prove this property. So the first one, so the alinearity, so see the last time. So we have shown this last time. So maybe,
Yes.
Yeah. So the invertibility. Now if I set C tilde Mn is this formula. R inverse like this. So Mn. Then I need to prove it is the inverse, so I compose with Cmn. So C tilde Mn C Mn, what is it? It is R, the flip, against the flip, and R inverse. Okay. So twice the flip cancel, so this is just R and R inverse. Now, by definition of an action, if I have twice the action, I have the product, so it is R inverse R. So here I have the product. So the product of the two is one, and now the product of the second one is here. So here this is because M and N are module. This is the axiom I recall during the notation. Twice the action is a product. But this, so this one, this is just R inverse times R. This is 1A tensor A. This is 1A tensor 1A in A tensor A. So this is equal to Mn, but the unit acts, so by the unit acts as the identity, so it is Mn, identity of M tensor. Okay. And likewise, similarly, we obtain that say Mn, C tilde Mn is identity of N tensor M. So thus we have shown the first. Now for the second. So F and G are a linear morphism. What does it mean in graphical terms? I can first, for example, for F, apply the action, and then apply F. But the same thing is I can just first apply F and then the action. M prime. So here's the action of M. This is action of M prime. So for F to be A-linear means this, and similarly for G. N prime. A, N. And thus, how do we verify this identity? Then what do we have? So C M prime N prime F times G. What is it? It is first we apply F G and the definition C. So like this. Okay. And then this. So M, N, N prime, N prime. So if I use this, so I can slide F. So this is equal to R. I have F, I have G, and then the flip. And finally, I can. So the flip is natural, of course. So since this G, F, R, and this is exactly G plus F, C, M. That's what we wanted to prove. Okay. So the first property. So C. The map C calls the binding. The binding is an linear isomorphism and is natural in M in N. M. So we also have the following property for A modules M N P. So we have first so Cm is Cmp identity of N. Identity of N Cmp and second Cm N plus P. This kind of multiplicativity with respect to the tensor product of the binding. So it is identity of N Cmp Cmn also identity of P. Okay. So let us quickly check this property, and we will see that we use all the action of an R matrix for the A-linearity of the binding CMN, we use that R delta of R. CMN is A-linear. For the invertibility of the R matrix, we use that epsilon times identity of R is the unit. And now we use for this property the last two axioms. Okay, so let us prove, for example, the first one. Okay, so I will compute this. C MP, so identity of N, C and P. What is it? It is, so I start with M and P. I first use R here, then the flip, and then I flip M and P. So I have R, and then I flip. Okay, this is this one. No, I can rewrite it like this. So I have twice R, and then I flip. So this one goes first here. This one go here. This one go here, and this one go here. Okay. Now I can use the axiom of an action on P. So I have this R. So I multiply the second one. And I use it like this. Okay. But now we know an axiom of the R matrix. So this one is this is equal to, so the coproduct R like this. So we have R coproduct this. Okay, so now so I recall that the action on M tensor N, how it is defined. So in graphical term, we have this A M tensor N. How do we define the action on a tensor product of two A modules? So we used the coproduct A M N. Yeah, recall that. And thus, this is equal to, we can see the action on M tensor N. Here I put M tensor N P, P M tensor N, and I put R. And this is exactly C M tensor N P. and that's what we do. So I leave you, so this, of course. Like this. So I leave you as an exercise to prove the second assertion. He used the second axiom like this. Okay. And now, finally, what now can we prove with this property? So maybe I use some notation. So we denote CMN like this. M, N, N, M, and its inverse, C, M, N inverse is like this. So N, M, M, N. Now we can, so this is just notation, we can traduce the property we have shown. What means naturality of C? It means this. So if I can slide a linear morphism like this, so this is the naturality of C. And then how do we traduce these properties? For the first one is, so the crossing on N tensor NP is the crossing MNP. Okay. And the second one is the other. MNP. Okay. It's just a traduction in graphical notation of the last two properties. Okay, so we're now ready to prove that this gives rise to solution of the Yang-Baxter equation. So, if I take for L modules M and P, what do we have? So, we have the third Reidemeister move, so what does it mean? So this one. M and P is M and P. So what does it mean? It means that, so identity of P times C, identity of P times C M N. Now, CMP times identity of N identity of N times C and P is equal to, so the other side, so what do we have? C and P times identity of M, identity of N, CMP, and CMN, identity of P. So in particular, now, for any A module M, CMM so if we take M equal N equal P, we obtain that CMM is a solution, is an A linear, and it is invertible, it is an isomorphism, solution of the Yang-Baxter equation. I recall it is CMM. CMM. So IDM. This is this equation for M equal N equal P. So this is CMM. Okay. Okay, we want. So here we produced solution of the Yang-Baxter equation.
So maybe the last term is.
Yeah, thanks. You have to. So we produce solution of the Yang-Baxter equation. So we just need to prove this relation. So we will use graphical notation to simplify. So this is the third Yang-Baxter mode. So we show this. So M N P. So by definition, this is C and P. This is C and P. Now we have seen with the last property that so here we have M and P, P and P and M. So this is equal to this. P tensor N, P times N. So here I put C and P N times P. Okay, so this is the last property, this one. Now, what can I do? We have seen that the braiding C is A-linear. So we can slide A-linear morphisms. C and P is A-linear. So we can slide, so we have this P and C and P M times P. And again, I use the last equation. So this, we can see like this. C and P. And this is exactly what we want. So to prove, you see that to prove this relation, we have used all the preceding properties.
But that third equality is by naturality of C, or...
Yeah, this is a braiding. And you can slide a linear morphism.
I mean, it's by naturality, not by linearity.
No, you can... No, C and P is a linear. This morphism is a linear, so you can slide it, okay?
Yeah, I see.
You cannot slide any K linear, but you can only slide a linear morphism. Okay, and so we have proved that quasi-triangular of algebra, if you have a quasi-triangular of algebra A and M module over A, then you have a solution of the Yang-Baxter. Now, as you can imagine, the question is, how do you obtain R matrices? So we obtain solution of the Yang-Baxter equation from R matrices. So how to produce R matrices? And now I will explain this. So I do not remember the number, but maybe this is maybe 5 or 6, I don't know. And we will see what is the Drinfeld double of algebra. Okay. So before defining what is a Drinfeld double, so we want to start from of algebra A and construct another of algebra dA, which is quasi-triangular, which has an R matrix. But now first I will define this notion. So let A and B be of algebras. So what I call a distributive law of B over C over A is a map, is a, let's say is a linear map, a K-linear map. We are over a field K that I call omega from B times A to A O times B, and I need that this map verifies these axioms. So alors, first, I want this. So what can I do? Okay. B, A, so I can take A, B. So A, B. What can I do here? I can just first say omega A, B, A, omega A, B. Okay. So if I want to write in usual terms, this is omega, if I compose with identity of B, would answer the multiplication of A. is just multiplication of A, the identity of B, compose the identity of A times omega, and omega times E, identity of A. Okay, now we have on the other side. How, if I use the multiplication of B, I impose that this relation. I can use omega, B, A, B, so AB, omega again. Okay. So I do not write in this term, but now, third action, I want some compatibilities with the unit. So if I plug the unit, so it is B, A, B, it is AB, and in the other way, if I plug the unit of B, is like this A, B, and I want also what do I want? For I want some compatibility of this omega with the coproduct. So I want omega to be a coalgebra morphism. So what does it mean? It means so if I plug omega and then the coproduct, it is the same as taking the coproducts, so A, B, so no, so this is B, A, B, A. So I have A, B here, so I have A, B, A, B. Here I have B, B, A, A. So A, B, A, B. And finally, I want if I plug B, A, B, is just so compatible with the co-units, B, A, like this. Okay, that's the definition. A distributive law is a map which satisfies these properties. And I state why we introduce this. So maybe before, for an example. So if I take the flip map, B, A, B is a distributive law of B over A. So you can think if you replace omega with the flip, you have a distributive law. Okay. So maybe we make the break, and after the break I will explain that such a distributive law produces Hopf algebras, a new Hopf algebra. Okay, maybe we make the break. Why is this is interesting? Such a distributive law distributive law. So then we can produce a new of algebra on the tensor product of A and B. So with product mu defined like this. So we need to define a product from A tensor B, A tensor B. So what do? We use the distributive law to permute A and B. And then we use the product of B here, the product of A. So the unit is just the product of the unit. So what is a coproduct? Just coproduct is just the usual coproduct A, B. Counit is the product of the counit, AB, and antipode is S of A. I did not plus. I explain the notation later. So here, okay, is the antipode of A. And I will denote with a minus is the inverse of the antipode of A. This is just antipode plus. Okay, so we produce a new of algebra. And we denote this of algebra to remember like this. As the vector space is just A tensor B, but the product is this one. Okay, let us quickly check this property. Okay, so we first prove that mu is associative. So what does it mean? So it means, so if I take 3 times AB, 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 so I can take mu, AB, and then mu, AB. And so I make computation so that I can slice it. So here, by definition, what is it? I plug omega. And then here I plug omega. Okay. Now here I can use the axiom of a distributive law here. On this part, I have an axiom for this. So I have omega So the axiom is so B A so BAA A B A B A B. So here I have omega and B. So this is this part. And then what do I have? This one. Okay. And now if I use the associativity of the product of A, here, what I can rewrite this like this. Okay. I do the same for the other. And we compute mu. So for this one, it is okay, and again I use the other axiom here for this. And what I get? On this side, so B A A I use here the action, and what you can see again, now I use associativity of B is again and here I use associativity, and presumably this is the same picture. Okay, and this is equal to this one. So we have shown that mu is associative. So now mu is unitary. So if I put mu and the unit, so what is it? Omega. We have an axiom here which says that it is simply this is identity of A tensor B, and similarly for the other one. So mu is unitary. Now, so the co-associativity and co-unitarity of this, we have already seen it. It's just the product of two coalgebras. What remains to prove is that the coproduct is multiplicative. So what does it mean? So we have delta. So we have delta mu. So if we compute this, so what is it? It is omega and then the coproduct. now we have axiom. So the multiplication, so the coproduct is multiplicative. So this is omega. Here we use, and again here. And now we twist like this. I use that the coproduct of A and B are multiplicative. No, I can twist here twice. Does not change. And I can use the axiom that delta is the morphism of coalgebra. So this is equal to what? Omega. So I apply the formula here. So I twist this and this. And I have again this. This. And so if you can see, you can slide. And so let us check it is equal to what we want. Okay, so we want now delta here we take the product and then mu that we want this equal to this, so we just write it is so we flip omega and here omega. And so if I did not mistake if I this is the same thing. I can slide this like this. So and it should be okay. So this is okay formed. This branch should be multiplied with the first output of this. This branch should multiply the first output. This is in third position. You can verify this is the same. And so this is indeed equal to star. This is just easy verification. Okay. And finally, epsilon is multiplicative. And we will see you use all the axiom. So what does it mean? Epsilon mu. So what is it? This. Well, the co-unit is always multiplicative, so we have this. But I use the axiom now. I think it's the fourth axiom for this, and what I get it is, which is indeed epsilon times epsilon. This is epsilon. Okay. And I leave you to verify that what I gave is antipode. Okay, so we define.
Sorry, so about co-associativity?
So the co-associativity we already used. So it's quite evident because it is just the product of two coalgebras is a coalgebra. But you can verify it. Data co-associative. So you can verify by hand if you want. But we already use this fact, actually. So I leave you as an exercise. But it is so the coproduct does not involve the distributive law. It's very easy to verify that. Okay. So now we have a way to produce of algebra, new of algebra if you have a distributive law. Okay, so now next, how to define multiplicative laws. So now we consider up pairing phi from B tensor A to K between B and A. So what does it mean? Phi is a k-linear map such that, okay, maybe I use color once to see the actions. So if I denote phi like this, so B is for red and A is for white. B tensor A, okay. So what do I want? I want, if I take the coproduct and then twice, I want this to be equal to first this, and then I take the product. No, I can take the product. And then the pairing, I want this to be equal to and here I use the opposite co-multiplication. And now just equal this, and now the other way around. Okay. So F pairing is a linear map which exchange multiplication and commultiplication this way. And we have the following way to define a distributive law. this property. Okay, so if given such of pairing, so the map, I can define the map omega like this. So maybe I use the following notation first. So I recall that co-associativity means, so if I take this equal to this one. And we denote this by this. This map, so this means this, and which is equal to this. Just a useful notation. And okay. So what do I take? 2 trinons like this. Here I take plus. And now I need to and I put the other. Okay. I do this. This is a map from B tensor A to A times B. And the key fact is this map is a distributive law of B over A. And before proving C, I will say that the associative, so the associative of algebra I will denote like d phi AB. It is A. Okay. So we have a distributive law, you have so we call it the generalized Greenfeld double. Okay, so we have, if we have off pairing like this, we have a new this of algebra. So this is here the distributive law associated to the off pairing phi. Okay, so what we need to prove is that this satisfies the action of a distributive law. Of course, we will use this. Okay. So this is some work. So okay, so we begin. So maybe we won't check all the action, but some. So there is one action which is this. So V A. And this should be equal to, so we use this, so we have, so now I forget the colors. This will be too long, so I just put, you remember when you have a cap like this, so this is just the pairing. So by definition, what do we have? We have yes. So this is the first. No, I again have plus. Sorry. So this is the first distributive law, bigger. Then consider distributive law here. So the first this is. Okay. So what to do? So the notation, I will again extend the notation, this notation here. If I have several, this means that I put several coproducts. And never mind which way I put the coproduct because of the associativity, co-associativity. Now I can slide this here. So what do I have? I have 1, 2, 3, 4, 5. And here I have 3 and 3. Now I have plus plus here. Then, so here, the two middle, I multiply them. Then this plus this minus here, so this plus here, this minus here. And then I swipe. Okay. Now, so this I can rewrite using the co-associativity like this. And now we know that the antipode is anti-co-multiplicative. So this means what? This means this equal to this. So I can replace this to this. So what do I obtain? So maybe I should englobe this crossing, it's better. Yeah. And so I remove this crossing here. Okay, so what do I obtain? So I obtain So on the middle, like this. So and now this one is on the first. This one is on the last. This one. This one is on the first. Here, this one is on the last. On the last. Okay. I do not see. Okay. So we have this. No, we need to check the other one. And we'll see if it is equal. So we want this equal to this. A, B. Okay. So by definition, what is it? It is. So you have it written like this. Okay. Now we will use that the coproduct of A is multiplicative. So what does it mean? So A, this is, for example, this. So here you use a multiplicativity, so it means this. And we use again the multiplicativity, so and if we use the notation we have, so we have this. Okay. So the multiplicativity of the coproduct implies this relation. So now we can replace it, this part here, using this. So what do we have? So, and then we have this is the first on the first, the third on the third. Now we can use the action of the pairing. And so the action, well, now recall, I use this is equal to this. This is the axiom of off-pairing. It's one of the axioms. So we can use no, sorry. This is the other way. We have this axiom. Oh. Here we are. This is for the product. We want to slide the product. So the product. So BAA is okay. The first one. Okay. So now I can slide this one. So I do it again. Okay, and this. No, if I slide this product, what do I obtain? A coproduct R. And if I slide this product, I obtain a coproduct there. And if I look, now I can slide this, and I obtain, hopefully, this one. Let us check. This on the first, this on the first. Yeah, so this is the same. And so it is equal to this morphine too. Okay, so we have shown one of the actions. So as you may see, this is a long way to prove, but it works. So maybe let us check another one, and then I will leave you to check the other. So we have that omega, among the actions, that omega is a coalgebra morphism. So what is it? So omega should be equal to this one. Okay, so let us check this. So this one, so what is it? So I will put the picture and modify. So because I have three dots, so it is something 6. A plus here. Now I have another 6. And then, so the first to the first, the third to the third, and I cross. The first to the first, the third to the third, and I cross. So this is this one. Now, so I can use the co-associativity. So I can modify this like this. And again, so this is these two branches. I can modify this like this. This is co-associativity. But now, I recall which one? I have this action. So BA is equal to the coproduct of A and product of B are related this way. So this here, what is the picture? Then I exchange. So if I, so what is it? It is now I use this action. So it is this one. And now if I use the axiom of an antipode, this is equal to this, and which is indeed equal to this. So this part here, I can write in maybe in blue or in green. I can remove. Here I have so I can remove this, and I replace this with two co-units, but co-units I can't forget them. So what I get is something like this. So 4 plus and so plus 1, the last one, and then I swap. But now if I write this, it is equal to this, and you can see this is exactly if I maybe I put too much here. Yeah, there is just you cross these two and these two. Okay. And if you slide this and this, you exactly have this. So we have proved the equality of this. Okay. So the other axiom has proved similarly. So now we have constructed a new alpha-algebra using an off-pairing between two alpha-algebras. Okay, so, and then we apply this to some specific pairing after the break. So I recall that today we have one more class. We will have one more hour today and the next week, and won't have class on Friday, 23rd of August. December.